Have you ever wondered if a new website design is actually better than the old one? Or if a new medicine really works? Or maybe if your latest marketing campaign brought in more customers than the last one? We all make guesses about these things. We might have a gut feeling. We might think, yeah, this new button looks nicer, so more people will probably click it. But in the world of data science, we don't like to just guess. We want to know for sure. We want to use data to make smart decisions. And that, my friends, is where hypothesis testing comes in. It's a superpower for data scientists. Hypothesis testing is a formal way to check if our ideas are supported by the data we have collected. Think of it like being a detective. You have a theory about what happened, but you can't just say, I think this person did it. You need to gather evidence. You need to analyze that evidence. And then, based on the strength of your evidence, you decide if your theory holds up. Hypothesis testing is the data detective's toolkit. It gives us a step-by-step process to follow. It helps us move from I think so to the data strongly suggests. It's the bridge from random guessing to informed data-driven decisions. So why is this so important? Imagine running a huge company. You're about to spend lakhs or crores on a new marketing plan. You wouldn't spend all that money on a gut feeling, would you? You'd want proof. Let's stop guessing and start knowing. Let's learn about hypothesis testing. All right, let's dive into the core of hypothesis testing. It all starts with two competing ideas, two opposite stories. We call them the null hypothesis and the alternative hypothesis. It sounds fancy, but the concept is super simple. The null hypothesis is like the default nothing new is happening idea. It's the status quo. It's the boring explanation. It often says there is no change, no difference, no effect. We write it down as H0. Think of it as the ho-hum hypothesis. Nothing exciting to see here, folks. For example, let's go back to our website button. The null hypothesis, H0, would be, the new button has no effect on the number of clicks. It performs exactly the same as the old button. On the other side, we have the hero of our story, the alternative hypothesis. This is the exciting idea. This is what we, the researchers, data scientists, usually hope is true. It's the hypothesis that says, hey, something is happening here. We write this one down as H1. It's the direct opposite of the null hypothesis. So for our website button example, the alternative hypothesis, H1, would be, the new button does have an effect on the number of clicks. Our goal in hypothesis testing is to see if we have enough evidence to reject the boring null hypothesis in favor of the exciting alternative hypothesis. Okay, so we have our two competing ideas, the null hypothesis, the boring one, the alternative hypothesis, the exciting one. Now, how do we decide between them? We collect data, of course. But then what? We need a way to measure how surprising our data is. That's where the p-value comes in. The p-value is one of the most important and often misunderstood concepts in statistics. But don't worry, we'll make it simple. The p-value is a number between 0 and 1. That's it, just a number. Let's think about what this number means. The p-value is the probability of seeing the data you collected, or something even more extreme, if the null hypothesis were true. Whoa, that's a mouthful. Let's break it down. Imagine the null hypothesis is true. So, our new website button really has no effect, but just by random chance, when we run our test, we might see a small difference. Maybe the new button gets a few more clicks just by luck. The p-value asks, if the button truly has no effect, what are the chances we'd see a difference as big as the one we just saw in our data, just due to random luck? A small p-value means our result is very surprising. It tells us that it would be very rare to see this kind of data if the null hypothesis were true. For example, if we get a p-value of 0.01, it means there's only a 1% chance of seeing our results if the button had no real effect. That's pretty surprising. It makes us doubt the null hypothesis. Maybe there really is an effect. On the other hand, a large p-value means our result is not surprising at all. If our p-value is, say, 0.60, it means there's a 60% chance of seeing our data just by random luck. That's not surprising at all. Small p-value equals surprising result, maybe reject H0. Large p-value equals not surprising, don't reject H0. Oh yeah. So, we have our p-value. It tells us how surprising our data is. A small p-value says super surprising. A large p-value says not surprising at all. But how small is small enough? Where do we draw the line? I can't just say 0.049 is small, but 0.051 is not. We need a clear rule. This is where the significance level comes in. The significance level is a threshold that we decide on before we even start our experiment. It's our pre-decided cutoff point for what we will consider surprising enough. The significance level is often called alpha, written as alpha. The most common value for alpha is 0.05 or 5%. This is just a tradition, but it's a very common one. By setting our alpha to 0.05, we are saying, I am willing to accept a 5% risk of being wrong when I say the null hypothesis is false. So, the rule is simple. If our calculated p-value is less than our chosen alpha, we declare the result statistically significant. If the p-value is greater than or equal to alpha, the result is not statistically significant. It's that clear. Let's use our alpha of 0.05. We run our experiment on the website button and calculate a p-value of 0.03. Now we compare. Is our p-value 0.03, less than our alpha 0.05? Yes, it is. So what do? We reject the null hypothesis. Now what if we ran the experiment and got a p-value of 0.25? Is 0.25 less than 0.05? No, it is not. So in this case, we fail to reject the null hypothesis. Notice the careful wording here. We don't accept the null hypothesis. It's like in a courtroom. Not guilty, not innocent. Making decisions using data is powerful, but it's not perfect. Because we're dealing with probabilities and samples, not the entire population, there's always a chance we can make a mistake. In hypothesis testing, there are two specific types of mistakes we can make. They have boring names, type 1 error, type 2 error, but the ideas behind them are important to understand. Let's start with a type 1 error. This happens when we reject the null hypothesis when it was actually true. A type 1 error, a false positive. The data told us something special was happening, but it was just a fluke. In our website button example, a type 1 error would be concluding that the new button increases clicks when in reality, it has no effect. We got excited, rejected the null hypothesis, and made a wrong decision. The probability of making a type 1 error is alpha. So if we set alpha to 0.05, we are knowingly taking a 5% risk. The second mistake is a type 2 error. This is the opposite. A type 2 error happens when we fail to reject the null hypothesis when it was actually false. This is a false negative. There was a real effect there, but our test wasn't powerful enough to detect it. Our data just wasn't surprising enough to cross the finish line. In our button example, this would mean the new button really is better, but our test results were weak, so we concluded there was no effect. We missed an opportunity. The probability of making a type 2 error is called beta. Unlike alpha, we don't set beta directly. It depends on things like how big the real effect is and how much data we collect, our sample size. There's a trade-off between type 1 and type 2 errors. If we make our alpha really small to avoid a false positive, we increase our chances of a false negative. It's a balancing act. We have to decide which error is worse for our specific situation. Is it worse to launch a useless feature or to miss out on a great one? This all might seem a bit abstract, but hypothesis testing is used every single day to make huge decisions in the real world. One of the most common applications is A/B testing. This is the bread and butter of online companies like Amazon, Netflix, Google. Imagine you're working for an e-commerce site. You want to know if changing the Buy Now button from green to orange will make more people buy things. You can't just change it and hope for the best. Instead, you run an A/B test. Group A, the control group, sees the old green button. Group B, the treatment group, sees the new orange button. You let the test run for a week, collecting data. Now you can use hypothesis testing. Your null hypothesis is the button color has no effect. Your alternative hypothesis is the orange button has a different purchase rate. You calculate your p-value, and if it's significant, you confidently switch to orange for everyone. This is how websites are constantly optimized for better performance. Another massive area is medical trials. When a pharmaceutical company develops a new drug for, let's say, high blood pressure, they must prove that it works and is safe. They conduct a clinical trial. One group of patients gets the new drug. Another group, the control group, gets a placebo, a sugar pill that does nothing. The null hypothesis is the new drug has no effect on blood pressure compared to the placebo. The alternative hypothesis is the new drug lowers blood pressure. The health and safety of millions of people depend on this test being done correctly. A low p-value here is literally a lifesaver. Finally, think about marketing. A company wants to know if a new TV ad is more effective than their old one. They can't ask everyone in the country, so they might run the new ad in one city, like Mumbai, and the old ad in a similar city, like Delhi, for a month. They then track sales in both cities. The null hypothesis would be the new ad has no effect on sales. The alternative hypothesis is the new ad increases sales. Based on the results of their hypothesis test, they can decide whether to spend crores launching the new ad campaign nationwide. From what you see online to the medicines you take, hypothesis testing is the hidden engine driving smart decisions everywhere. Enough talk, let's do some science. Let's see how easy it is to perform a hypothesis test using Python. We'll use a very common test called an independent samples t-test. This test compares the means of two independent groups. We'll use the SciPy library, which is a fantastic tool for scientific computing in Python. First, let's set up our scenario. Imagine we ran our A/B test for the website button. We have two lists of data. Each number represents the number of daily clicks for that group. Group A saw the old green button. Group B saw the new orange button. We want to know if the average number of clicks for Group B is significantly higher than for Group A. Okay, we have our data. Just by looking at the numbers, it seems like Group B has more clicks. The average for Group A is around 103.7. For Group B, it's around 118.1. But is this difference statistically significant, or could it just be due to random chance? Let's define our hypotheses. H0. There is no difference in the average clicks between the two groups. H1. There is a difference. Now, let's run the t-test. The t-test underscore in function in SciPy makes this incredibly easy. Now for the big moment. The code will run the test and give us back two numbers. The t-statistic, which tells us the size of the difference, and the p-value. In this case, the output will show a p-value that is very, very small, something like 0.0001. We then compare this to our chosen significance level, alpha. Let's use the standard alpha of 0.05. Since our p-value is much smaller than our alpha, we can confidently reject the null hypothesis. The result is highly statistically significant. We have strong evidence that the new orange button really does lead to more clicks. Look at that. You just did data science. And just like that, you've taken a huge step into the world of data science. We've demystified hypothesis testing. Holy cow, StatQuest!